And welcome to another edition of Terms Defined. Here we're going to be defining the term cosmology. And it's also a cosmology segment. And I'd like to welcome the guest, Eugene Bagashov, who has been on quite a bit of videos lately. Say hello to Eugene. I think you should be able to be well heard.
Hello, everyone. I'm Eugene. Nice to meet you, I guess.
And he's joining us via Skype here on the newly revised Smash News Network. So we're not trying to cover up Skype there, but in any case, I'm your host Dan, aka smAsho, and we do daily space weather videos. And I think one of the oddities of cosmology is that a lot of other sciences are based on it. So essentially, for example, geology ties into cosmology because the theories about the layers of the Earth and how the Earth's geomagnetic environment is formed and so on are all sort of tied in together. There's a whole bunch of branches of physics and stuff that are sort of tied together and perhaps have been leading people down some bad roads. What say you, Eugene?
Well, certainly, yeah. I mean, that's a really good point you started on that. I guess one might think that cosmology is something very distant and unrelated to us, but unfortunately, I should say it is pretty related to even down to earth, no pun intended, sciences like geology. Because let's say, for example, the abundances of chemical elements that are quote unquote supposed to be there are estimated via cosmological processes in the first place. You probably know about the idea that the sun isn't the so-called first generation star because blah blah blah, because it shouldn't have as much heavy elements as it does, so these because it cannot synthesize them as according to nuclear fusion model, so it should have had those elements initially from other stars which were the first generation, and so on and so forth. And the datings in geology, for example, are heavily reliant on all this modeling, starting from cosmology, essentially. And when I say starting, I already mean that we currently have this cosmological model which assumes that there was a start to the universe, so to speak, which is the Big Bang, obviously.
Sure.
So all of that is connected. And much more than that, I would say even the particle physics theory is also heavily reliant on cosmological observations, or at least supposedly the observations we have, which supposedly have connection to the cosmology. And some, let's say, well, just not to go far, for an example, the theory about neutrino physics, like weak interaction physics, it's heavily dependent on cosmological observations. Like, people say, okay, what if such a neutrino exists, let's say, and they say, oh, that contradicts cosmological observations. Okay, so we'll throw that out and won't discuss it anymore, etc., etc. So yeah, basically, if we have the cosmological picture wrong, which, spoiler alert, I think we do, then all those other areas would also be at least questionable, at least a lot of things they state. Let's say geology, particle physics, what else? Well, probably
almost all of it.
Almost
all of physics, because when you base an assumption upon an assumption upon assumption, and 2 generations into 4 assumptions, you've got one thing off by an order of magnitude. Your models, and as we've come to see all too personally in the past 6 months or so, how often a model can be. So the way pandemic models have been forecasted in places like the UK and indeed the US as well. If you're off by a little bit, and then you're protracting that out over 1 billion years or 4 billion years or however many billion years, your miscalculations may be beyond the pale.
Yeah,
And I
yeah,
think
of
chemical
course.
abundances are a very interesting thing that we look at, in cosmology. One of the things that sort of refutes all of the information about how these things accrete, how things like stars form, if they form in the first place. Uh, Whatever's going on with them, the chemical abundances that we see does not really follow suit with the expected ages of things. So the more we look at the really close up spectroscopy of things like the environments around odd stars, we find strange heavy metal abundances in those places. And just to clarify, in cosmology, when we say metals, we mean everything more massive than lithium on the periodic chart. So, and
Well,
that's another important distinction, because the idea that perhaps the heavier elements are coming out of atmospheres of stars instead of out of their cores is pretty serious. And the implications, of course, on the rest of sort of gravitational accretion cosmology, which determines things like the mass of things inside the Earth. If those are completely misunderstood, then all the dating of everything and the entire sort of basis for which many branches of especially, I guess you could say, the natural sciences. So in some ways, lab science is sort of, I guess it is actually leading the way in some ways.
I just wanted to quickly correct you because it's not just beyond lithium, it's including lithium. So, lithium is actually a
Right,
metal in
right.
chemical sense, but it's also a metal in astronomical sense.
Yeah, no, you're right.
And and lithium is actually curious in this regard because there is a famous lithium problem in cosmology and astrophysics in general, because it seems like, according to the, let's say, models of nucleosynthesis, which is basically how the heavier elements are produced from lighter elements, in the Big Bang cosmology, there is a problem with the lack of lithium that we observe. So we observe too little of lithium than should be there, according to this model.
Yeah, yeah.
Uh,
So let me just correct myself. Yeah, everything to the right of helium on the periodic chart. So lithium,
well, to the right of
inclusively lithium.
helium, there's nothing because it's the last one in the first row. Uh, so below helium, let's
Yes,
say.
more massive than helium. The point is,
Yeah.
there in cosmology we've got what cosmologists call first generation and second generation stars, and in the first generation stars you've got just a hydrogen to helium star, and then with other different stars that are older and of different various properties, for some reason they decide to produce heavier elements. And this is sort of breaking down, like the more radio spectroscopy we do, and we look at this strange abundance of hydrogen coming out of galactic jets and stuff, we're not seeing the evidence that we ought to see if heavy elements came out of supernoval explosions. We're just not seeing that. And I think Eugene would probably agree, although I don't think we've discussed this ever. I'm not scared to go out on a limb because there are lots of limbs to go out on.
Hmm. Well, I just wanted to. Well, I'm not sure if this is relevant, but I just wanted to mention that there are, let's say, alternative theories for this solving of this lithium problem. For example, the Pierre-Marie Robitaille's stellar model, like the model of the liquid hydrogen sun, it states that the lithium is retained in stars because it helps them to sustain their hydrogen lattice. Well, it's his answer to this problem anyway. So my point here, I
In
guess,
some
is
in
that
some part of the atmosphere, you're not talking about the internals. You're talking about
no,
some place on the outside, right?
I'm actually talking about the internal structure of the star itself.
Oh,
So
okay.
it's not observed on the surface exactly because it's retained inside, so that it could theoretically help. And there are some references he points to, which say that indeed lithium helps metallic hydrogen to form.
Yeah,
But
it could,
anyway,
and we
my
really
point
don't
is
know what
that
happens to certain elements when you take a distinct element and you put it in millions of atmospheres. It's sort of one of the most emerging branches of science now, because we don't really fully understand the properties of that stuff. and that totally changes the cosmology of what's going on inside of a star.
We don't even know, strictly speaking, what kind of pressures there are.
That's
Like,
true. Yeah.
it can be anything. I mean, for what we know, the star might be completely hollow. It might be like 1,000-kilometer layer of luminous stuff, and who knows? I mean, I'm very, very, very skeptical about anything in this regard, because I think, although that kind of sounds arrogant, but I think I understand how easily misled you may be and easily convinced of your own models, and
Oh,
like
sure. Yeah. Oh, absolutely.
any observation, strictly
100%.
speaking, can have infinite number of interpretations. And if you have a theory that you kind of impose onto the observation in the first place, then you would have a sort of a confirmation bias, etc. And blah blah
Absolutely.
blah. So that's a whole separate discussion anyway. So my point about Robitaille was that there are many alternative theories that we can have with regards to these abundance, let's say, miscalculations, I guess,
Yeah, you could
etc.
say miscalculations. I mean, yeah, it's if stars are producing heavy elements someplace besides in their cores during, what are referred to as supernoval explosions, which, by the way, one of the many things that doesn't seem to be answered at all by the classical astronomy explanation of things is the fact that in most supernoval nebulae we see a star in the middle of it. So it's like, oh, this is the end of life event that causes heavy elements to form where a star explodes, except that there's still a star inside of most of those supernova, quote, remnants, end quote.
Well,
It's like they're all
unfortunately,
novas.
I'm not a specialist in this area, so I can only say that I think, from like what I vaguely remember, what I've read, etc., is that there may be types of supernovae where supposedly, again, it's all a model and a hypothesis, that they're like the external layer sort of blows outwards, whereas the internal layers are kind of squashed inwards during the same process. And so, well, so there is some remnant because of that, uh, but that's, again, I'm not a specialist in this area, so don't take my word as anything serious, but I think that's the explanation they
Well,
have.
we see odd chemical spectra coming out of a lot of the situations. So you'll see novel shells, and then years later you'll see a star re-illuminate in the area, suggesting that you were having the star in the middle of that novel shell obscured by the dust cloud that it creates. But still, I mean, ultimately, what we really see in the most large scale cosmology is giant plumes of hydrogen. We see lots of hydrogen in places where you would expect all of these violent explosions happening to show you lots of heavy elements, but we just see lots of hydrogen. Galactic scale jets and so on. And another issue I have with cosmology, and this is a huge one, is the term, what do they call it? Stellar breeding grounds, stellar nurseries, places where stars are being born. People think that just because you see X-rays there, that stars must be forming in those regions, which seems like a ridiculous notion to me.
Well, I would agree. I mean, in general, I would make such a comment that any sort of processes that take a lot of time, which means like at least hundreds of thousands of years, are only hypothetical. Like, we cannot observe them.
Right.
I mean, in our lifespan, let's say, like, for how long do we have this X-ray instrumentation, for example? That's roughly 60 years, maybe, in space. So, well, because the atmosphere of Earth absorbs X-rays. So anyway, even speaking about galaxies, we don't really observe galaxies rotating, right? We only see Doppler shifts from their edges, so we only assume that the galaxies rotate, but strictly speaking, we don't know that. If we come, if we go full on skeptical kind of
which is
philosophy here.
for the viewers just to say that the objects on the edges of the galaxies appear to be on one side moving toward us and on the other side away from us based on the expected light curve from those portions of the spectra, correct?
Yeah, so on one side we see them kind of bluish, so they're assumed. So they're the emission lines are or absorption lines or whatnot are shifted towards the shorter wavelengths. So that is assumed to be a sign of the Doppler shift, which means they are moving towards us. Whereas if they're shifted towards the longer wavelengths, it means they're moving away from us.
And I think
that's how we assume that the galaxies rotate. But strictly speaking, this is not proven that the galaxies rotate in the first place.
Right,
but
right.
that might be too hardcore of a skepticism, but
no, it's not. It's not. Mind. I mean, redshift is a problem. Redshift is a problem. But it's fairly accepted that these objects are moving at fairly high speeds in relation to each other. In other words, galaxy A versus B, certain stars within the galaxy, and so on. You're talking about hundreds of thousands of miles per hour here. Multiple times the speed of your average meteor entering the Earth's atmosphere. So that, there are some relative velocities out there that are very, very high.
Yeah, I just kind of out of curiosity, I just thought about that. Maybe you can develop a theory of a non-rotating galaxy, and you would be fine with it. And, I think it's plausible. I mean, who knows? I mean, given the problems that we do have with the rotation of galaxies, I mean, speaking about dark matter problem and things like that, I mean, why not? I mean, people invent all kinds of alternative theories of gravity and the theory of dark matter in the first place, and that's kind of what is called new physics. We already need to go beyond what is known, again in air quotes. So who knows, maybe even such a theory may succeed, that the galaxies don't even rotate in the first place. And these red shifts and blue shifts are caused by some yet unknown effect or whatever.
Yeah, maybe it could be some sort of a thing like the Faraday effect. The Faraday effect has the ability to, if you've got light shining through a magnetic field affected by matter in the magnetic field, you're going to get this absorption, or you could say refraction, depending on sort of which school of physics you're coming from. And that, I think that seems to be a thing too, because the more detailed we seem to look at certain objects, the dark matter, the quote dark matter end quote, doesn't seem to be distributed where it ought to be as per the gravitational movements of the objects seen. And it looks,
well,
the more I look at it, the more it looks like
also quote unquote.
Yeah, well, yeah, but the more I look at the light, like the quote lensing end quote, the more it looks like the Faraday effect, and the less it looks like what would be a gravitational lensing. I'm not convinced. Well, maybe you don't know, but I'm not convinced on the gravitational lensing.
I just want to quickly mention that Faraday effect is actually about the rotation of the polarization of light. So the thing is that an electromagnetic wave is a transverse wave that, well, it's kind of hard to explain, but anyway, it might be, let's say, the simplest case is that it's linearly polarized, which means that, let's say, the electric field vector oscillates along, let's say, z-axis, so
Okay.
up and down, let's say, and the magnetic field oscillates perpendicular to that, let's say, along y-axis.
Right.
So kind of left and right. So
like,
that's a
like the Hall effect.
Linearly polarized photon or electromagnetic wave. And Faraday effect, what it does is that, well, it basically says if you have a magnetic field along this wave, then it's going to rotate. So the electric field of the wave itself would start rotating, and the magnetic field too. So they would no longer oscillate along z or y, but the axes along which they oscillate would turn.
Yeah.
So this is what the Faraday effect is. It doesn't change the intensity of light, so it's not like an absorption or whatever. It just changes the properties of the light wave itself,
No,
like this.
I was saying adsorption, not abs with a D. Adsorption. In other words,
Well, I have no
some of
idea
the
what it
energy.
means in this context, but anyway,
Well,
no, it doesn't. It doesn't change the energy, the Faraday effect. Like the wave remains the same in terms of energy and momentum and things like that. That's what I was saying. So, but anyway, there was some other thing I wanted to mention, but I kind of forgot. You were talking about the Faraday effect.
well, that's okay.
But
There's also the Hall effect. This does make things react with each other at a 90-degree angle, like you were saying. The electric field would be perpendicular to the magnetic field, and so on. But
yeah, the
one of the
Hall
things,
effect is basically the effect on which our electricity generation is based on. Like, if you like throw a bunch of charged particles through a magnetic field, they would separate naturally because the positive and negative charges would kind of rotate around this magnetic field in opposite directions. So the positive charges would accumulate on one side, let's say, if you have a chamber, and the negatives on the other side. So that's how we actually get our potential difference, our voltage at our power station, power plant.
sure. So one of the other things I wanted to touch on was the fact that you don't like cosmology. Tell us about why it is that you're not a fan of cosmology. And I think we've sort of touched on some of the details of the stuff because we're like real science nerds, so we like care about the real details. Can you like help impart to the viewers why it is that you consider cosmology a term that could make you as a PhD candidate dirty? Like, don't befoul yourself, Eugene. Can you sort of explain that a little bit, unpack that, because I think people
Mm-hmm.
might think cosmology is just pretty old every day looking at the stars, and they don't understand sort of the conflicts between the physics that you'd call a quote unified theory, right?
Yeah, well, it's actually pretty simple. Well, first of all, and it's actually a kind of a separate question, but I wish to address it right here because I think it's somewhat important that the current term that we use with regards to this, let's say, field of knowledge is cosmology, which, strictly speaking, means the, let's say, science, or at least like the knowledge about how the cosmos, i.e., universe, operates,
Yeah, the
right? This is
origin and structure of
cosmology.
the universe. The
Yes,
origin and
but
structure of the universe.
well, more like how it works, like what is it about, let's say. But
Yeah,
what we have today as the main, like mainstream, again in air quotes, cosmological theory is the theory of a Big Bang. I would actually call it a hypothesis, but anyway, let's
yeah,
call it
yeah.
a
No,
theory
I
for
agree.
the
I agree.
argument's sake. So what Big Bang is essentially is a cosmogony, I would say, which means how the cosmos, i.e., the universe, began, like, how it came into being, So that
Right,
there's
right.
like a slight philological difference
As
between
if that's more important
cosmology
than
and
how it actually
cosmogony.
works, right? Like,
Yeah,
is it
so
more important how it
cosmogony is
works or how it came to exist?
Yeah, so Big Bang, I would say, is a cosmogony, and cosmology is how things work right now, whereas cosmogony is how things began, which is Big Bang. So there's a difference in this respect. But anyway, my, let's say, disrespect towards cosmology comes from the very simple realization that there is simply too little of uh, observational things that we can have about the universe, and the multiplicity of the possible interpretations of these little observations we have are almost limitless. So firstly, you
Yeah, that's a
cannot
good point.
have a cosmological experiment. So it already kind of brings into doubt the whole idea of cosmology as science, because in science, as again Francis Bacon and all those empiricists in 17th century claimed, in science you need to have experiments, because otherwise, well,
Yeah,
what are you
yeah.
going to do? You just have something that you can look at, but you cannot, roughly speaking, interact with. You cannot ask questions in
Yeah.
philosophical
And can I
sense.
just interrupt
So
you? Can I just interrupt you for a second? Hold that
yeah,
thought.
of course.
And this is one of the issues that I think you and Robitaille and I all share, because there's some point when you start measuring things, when you go, what is it that you think that you're measuring? And this kind of just goes on and on. And I think in cosmology and astronomy, it's the most insane of all, because you there's a point where you say, in order to get that measurement, what could possibly have happened? And this is sort of like an ongoing theme.
Yeah, so basically my main problem with cosmology is that, uh, roughly speaking, if you misinterpret the universe wouldn't, come to you and slap you in the face for it, for
Right?
misinterpreting it, because the
Right?
universe doesn't really care what you think about it.
Yeah, yeah.
Whereas if you, let's say, misinterpret how, I don't know, the brakes on your car work, then you might die, and
Or
that
how
would
your
be very
girlfriend will
serious.
react to you not fixing your
Yeah.
brakes or something.
Whereas, the Sagittarius A, asterisk wouldn't come to you and say, you know what, my
Yeah.
whatever X-ray emission is actually not caused by nuclear fusion or whatever.
I've been
Uh,
producing lithium in my atmosphere.
yeah, how could you not see that anymore? So
Exactly.
this extreme, I would say, removal of observations versus models is what makes cosmology almost not science. Like, I would
Yeah,
say,
yeah. It's
kind
damn
of
close.
on the verge of science in the first place.
Yeah,
So,
yep.
and actually, Alfvén, in his one of his books, I don't quite remember which one. I don't quite remember the title, unfortunately, but
That's
the
okay.
book where he talks about this
We can put it in the
blind.
comments later.
Yeah, of course, I'll send it to you. So he talks that about the fact that indeed cosmology is almost like, somewhere in between, let's say, science, religion, and philosophy. It's
Yeah,
somewhere in this,
yeah.
wicked realm.
Oh,
So
yeah.
yeah,
Oh my God, there's a lot of things that are shaped a certain way, which means it must be God. God must be a spiral. God must be a fractal, yada, yada, yada.
yeah, and it's
It's,
actually it kind of takes a funny forms
it
in
does.
certain respects. Like, maybe you remember this book by Dan Brown and this famous movie like Angels and Demons, where this, whatever, there's like a complicated plot there, but
I kind of know about
one
it,
of
yeah.
one of the main ideas is that the one of the physicists at CERN, at LHC, I guess, or whatever, they kind of wanted to contact with the Pope, to say that, oh yeah, the Big Bang is like a creation and whatever. And it's kind of very funny because it's kind of the reverse engineering of the very idea of the Big Bang, because, well, the idea of the Big Bang appeared as an attempt at justification of, this process of creation, because again, it was, and it's not a big secret, it was proposed by a Catholic priest, this Georges Lemaitre guy. I think he's Belgian, but whatever.
All
So
right, it's okay.
it's kind of, kind of Ouroboros kind of thing, the idea biting its own tail. So, kind of like physicists finally, realizing that their ideas come from religious thought, and kind of going back to the religion, in some sense. So, but yeah, but anyway, my point is that it's not science strictly speaking, cosmology.
It's almost
Uh,
like climate change, where you've got this self-perpetuating nonsense where you can go, oh, look at all this nonsense we've interpreted
yeah,
this way,
yeah,
which is
yeah.
totally inappropriate to what could possibly cause that to be
Hmm.
observed. And now we're gonna just gonna advance based on these assumptions, just on and on and on for hundreds. The idea that there's a fusion core inside the sun dates back to the 1800s. It's shocking.
Yeah, I actually think that you are correct here, that indeed they are similar. I mean, cosmology and climate science, but they are similar in the way that their models, let's say, are removed. And again, we cannot really make experiments in climate.
It's like oh,
That's
hey,
one
look,
similarity at least.
CO2 must be causing this, dark matter must be causing that. It's a perfect anagram. I mean, it's
Yeah,
a
yeah,
proper
yeah.
analogy, right?
Yeah, yeah. In this sense, I agree. But on the other hand, there are also differences between them in the sense that in cosmology, this removal of, let's say, observations from models is caused by the, let's say, hugeness of the whole system, right? Because, well, we are observing it from the inside, so to speak,
Yeah, in
in
some
all
cases.
directions for billions of light years. Whereas in climate, it's caused, I mean, the fundamental unpredictability, let's say, of the system is caused by the complexity of the system itself. So even though we can observe the Earth from outside, even right now, we still cannot understand how it really operates because it's so damn complicated internally. So yeah, but
Yeah, for sure.
fundamentally, the problem is the same, that we don't really have any sort of, kind of a lever or lever, if you're an American, I guess, how to, let's say, uh, get a like a strict correlation between the input and output,
Right.
so
Yeah. Yeah. Garbage in,
um,
garbage out with any computer model. I used to be a programmer in high school and early college days, and I used to write code, and it's a well known thing. Garbage in, garbage out. You put in bad input, and the math is done right, and the output is garbage because you put in bad code in the first place. The computer doesn't make a mistake, but if you don't understand the way the variables relate to each other, it's not helpful.
yeah, that's one problem, and another problem is kind of a more philosophical, and I'm not sure if other people would support me on this, but I still think that there is a big, let's say, danger in trying to apply our own, even laws of physics in the first place, to processes and scales we don't really comprehend. Like,
Like the
uh,
jets of M87, for instance.
yeah, can we really, let's say, scale it down? Well, sort of like aesthetically, philosophically speaking, can we scale it down to fit on our, uh, uh, you know, A4 sheet paper, and say that, okay, it's just that, it's the real scale is 10 to the 30th power larger and whatever, and we'll just compute it as if it was this small,
Right, right.
because a lot of processes, I would think, are different on these larger scales, and we have no idea. Again, it's just a natural skeptic's approach that we have no idea how they really work. Uh, but I mean, do we are we really confident that, let's say, Newton's gravitation is the same beyond, let's say, 100 astronomical units? We don't
Sure,
know
right,
that.
right,
And we
exactly.
have no way of
Yeah,
confirming that or disproving that.
yeah.
Are we confident that, let's say, Faraday's law or Ampere's law or Lorenz's force, etc., are correct beyond 100 astronomical units? We don't know that.
Yeah, I agree.
It's just, and whatever. So this is, again, the problem I have with cosmology, is that it works with things, it deals with things that are so far beyond our comprehension and even the possibility of interaction with them, that it's basically pointless in
Right,
some
and
very fundamental sense.
even at more local spots, I put up a graphic here. The area just south of and just north of the sun's poles is probably a completely different environment. There's like a crazy tube of energy, and there's like a enduring coronal hole in those places. And yeah, perspective is a big deal in space. If you're looking at a galaxy edge on versus across its plane, it looks completely different. You see a cigar-shaped pile of dust versus the brightest object ever imaged. If you're looking at it down the poloidal field line, which would be like a blazar or a quasar, depending on how aimed that jet is. So I think there's a ton of work to be done. I think it's sort of a good thing that cosmology is so bad. But I should definitely recommend for everybody to tune into Eugene the Philostopher, and it's spelled Philostopher. There's a T in there, Philostopher. So don't get confused about that. Go subscribe over there.
Yeah, I
Is there
actually
a
have a
URL?
video specifically about cosmology where I talk about the well, it's called logical cosmology. I'm not even sure if you'll be able to find it because it's not very new one. Like it may be, I don't know how long. When did I make it? But
Anyway, there's a lot of videos there, folks. And if you
yeah.
go
So
check out Eugene the Philostopher, just do a search for it on YouTube. There's not that many philosophers, and he's the best one since somebody who was it?
Quentin Robert Dineen. But anyway, so I just wanted to finish my sentence. So in
Yeah,
this
yeah, no, go on.
video, logical cosmology, I talk about, I specifically address the questions like how many universes are there? Is there a parallel universe, etc.? Like what is the size of the universe, etc.? And I claim that you can actually answer all those questions just logically, like defining all the statements, etc., and kind of working with them by the rules of usual logic. So I encourage you to watch this video, which again is called Logical Cosmology.
Yeah, and we're going to link to that in the comments. So anything else you want to add about terms defined cosmology? I mean, we definitely went on some tangents here. I think a lot of viewers should be interested. And hey, more tangents to follow, I think. Hopefully you won't have to evacuate your country there. We hope you don't experience things like hyperinflation.
Well, okay. Well, there are many things we didn't really touch upon, but like, for example, one of the fundamental assumptions in the current cosmological model is that the universe is homogeneous, so it's like everywhere the same, whereas alternative versions of cosmology, let's say, such as plasma cosmology, etc., they are more in line with the idea that the universe is highly non-homogeneous, which means that there are huge concentrations of matter and huge voids
Yeah,
in
well,
between them, etc., etc. So
definitely
uh,
voids. Yeah. Yeah,
yeah,
definitely
so there
both.
are many, many, many possibilities that we have, and all of them, or at least many of them, can explain the same set of observational data that we have. So, and like, I guess I would just state that I would ask you to believe me, but if you don't, there is still I can send you the links and whatnot that, let's say, for example, the cosmological so-called redshift can be explained by other mechanisms, let's say interaction of light with plasma, intergalactic plasma, etc.,
Agreed.
or things like let's say cosmic microwave background can be explained by the just the emission of stellar light itself, etc. And the
Absolutely. Yep.
Olbers, things like Olbers paradox, which is currently explained by the Big Bang, can be also explained by other things such as non-homogeneous character of the universe again, and blah, blah, blah. So roughly speaking, basically my main statement, I guess, here would be that the Big Bang model, or hypothesis, if you like, is not better currently than the model of, let's say, roughly speaking, infinite and eternal universe. Like they are equivalent in their strength in terms of explaining the observations currently, at least. So that would be my main statement that I would like to make about cosmology.
All right. Well, we thank you for that. And, part of the reason why we make daily space weather videos is because we consider earth science and heliophysics part of cosmology. And, of course, there's various different viewpoints from that. You can consider only galactic scale stuff as cosmology or whatever. And you may not be aware that I
Well,
actually considered a degree in cosmology, but at the time in the mid 90s, it was not a bright route to take.
I actually want to make another comment about this. I'm a theoretical physicist by training. Like professional training in the university, etc. So my teacher, he actually, the lecturer, he was lecturing me on special relativity and things like that. So one of his main statements about cosmology was that in cosmology, we actually consider a galaxy as a dot, basically. So this is the scale of cosmology. So when we're talking about galactic physics, it's actually more of an astrophysics than cosmology. This is just a point I wanted to make with regards to what you said previously. So cosmology is bigger than galaxies. Like the galaxy is like a material dot for cosmology. But anyway, that doesn't really change anything we talked about previously.
I'm sorry, did you ask a question?
No. I finished my sentence.
Oh. All right. Well, I don't know what else to add. Anything else you've got to add? It's about time to close this thing out. And keep in mind there will be more cosmology segments to come on the channel in the future. This is more of a terms defined here. And geez, we definitely went on some. We went down some rabbit holes, I think. And thanks for being a spelunker, I guess I should say.
Yeah, thanks that we didn't go into wormholes. Rabbit holes are okay.
That's part of your multiverse theory.
I don't have a multiverse theory. I think we have only one universe. And again, see my videological cosmology to know why.
All right, we're going to tune in. Again, look for all that stuff in the comments. Thanks again, Eugene. And let's close this thing out. We'll talk to you next time, terms defined and on cosmology segments. Cheers.
Goodbye.